Hi, this is Mrs. Vrobel. This is Chapter 5, Electrons and Atoms, Part 3. So in this video, we're going to talk about applying the Pauli exclusion principle, the Aufbau principle, and Hund's rule to write electron configurations. And we're going to look at orbital diagrams and electron configurations. Then we're going to look at determining valence electrons and drawing electron dot diagrams to represent an atom's outer electrons. Okay, so looking back at the previous video, we talked about Schrödinger and him representing the probability of an electron occupying space. Well, this space is what we call the atomic orbital. So notice that all those dots, if we were to include it in this one area, that's the probability of an electron in that orbital. Now, the interesting thing is we can actually organize electrons depending on the levels that they occupy. Notice that this big triangle, for each level, it has a certain amount of spaces in it. So the first level has 1 space, the second level has 2 spaces, the third level has 3, and so on. And we'll look at why that's happening. So in the second sublevel, we actually have 2 different types of orbitals. We have the s orbital and we have the p orbital. Now notice in the p orbital there are 3 coordinates that we can list for those specific p orbitals, and I'll show you in a minute what I mean. So here we have drawings, and these are actually mathematical drawings of the probability of an electron occupying that space. So notice in the p orbital there are 3 orientations. So it could be X, it could be Y, or it could be Z. And these are the spaces that the electrons occupy in those sub-levels or those orientations. Notice that with D we have 5 possibilities, and with F we have 7 possibilities. If we were to layer all the orbitals, so notice that when you go in the middle here, this is the 1s orbital, and it's smaller in size, and then layered on top of it is the p orbitals, and then we could go even further out with the s orbital at the 2 sublevel. Okay, so notice that as you go from a smaller energy level to a higher energy level, the bigger the orbital. Okay, now there's something else that scientists use as a convention. It's what they call spin. Now they sort of liken it to a planet on its axis. So an electron can have a clockwise or a counterclockwise spin. You're going to find within an orbital they have to have opposite spins. There's no way that electrons can have the same type of spin. So the arrangement of the electrons in an atom is what we call electron configuration. And notice the bigger the atom, the more electrons, the bigger the electron configuration. Now there's a principle called the Aufbau principle, and what it states is that electrons, they will go from a low energy level to a higher energy level when they fill up an atom. So it's sort of like a bus. When electrons get onto the bus, they occupy the lower energy states first. So they go to 1s. When that's full, they go to 2s. When that's full, they'll go to 3s. So notice that they fill up in order, and it's always lower energy level to higher energy level. Okay, so the first rule is the Aufbau principle. The Aufbau principle says that electrons have to enter the energy level of the lowest energy level first. So always go from the lowest energy level before you start filling in the higher energy levels. The second rule is what we call Hund's rule. And Hund's rule, when you have an orbital that has equal energy, the electrons will occupy each type of orbital first before they start pairing up. And I'll show you an example of that in a minute here. The Pauli exclusion principle says that no 2 electrons can have the same set of quantum numbers, and we'll talk about more of that in class. But notice that you can also have no more than 2 electrons per orbital. So what does that mean? Well, here we have a set of atoms. The first one is hydrogen. notice that hydrogen only has one electron. So as a result, it's only going to fill one electron in one orbital. And the notation is 1s1. Helium has two electrons. Now notice that they're paired up and they're in opposite spins. And as a result of it, we call that 1s2. So the superscript, which is the higher number, that represents the number of electrons total in that orbital. Here we have lithium. It has 3 electrons, so it's going to pair up electrons first in the 1s, and then it has 1 left over, so it's going to fill in 1 electron for the s orbital. And the notation here is 1s2, because there's 2 electrons in that first orbital, and then there's only 1 in the second orbital. Now let's jump down to nitrogen. Now notice nitrogen, it has enough electrons to first fill the 1s orbital, and then it fills the 2s orbital. But in the p orbitals, it has 3 types of p orbitals, and they're the same energy. So as a result, they're going to fill in 1 electron first with each orbital. They're not going to pair up with the first p orbital. Okay, that does not happen. And when we look at the notation, it's 1s2, 2s2, and then 2p3. So that 3 represents the number of electrons in that p orbital. Now when you jump down to oxygen, notice with oxygen, because there's another electron left over in the p orbitals, it can then first pair up with that p orbital at the beginning. And notice that the p orbital contains 4 electrons as a result of that. Okay, so this is how we represent the periodic table. We can actually color code it, and we can show the different electron orbitals. Now, where you see 2p, that last electron, depending on what element it is, if it's boron here, it has a 2p1 electron. If it's all the way over here with neon, it's a 2p6 electron. And these are the outer electrons that are found in those atomic orbitals. So valence electrons we call electrons in the outermost orbital. So it's the last electron that entered that orbital. And it typically is the highest energy level in that atom. Now, we talked about atomic orbitals, we talked about electron configuration. Now we're talking about electron dots. So we can actually use a symbol, and we can surround it with dots to represent valence electrons. And the reason why we're going to do this is we want to show bonding eventually, and we need valence electrons to show bonding. So this is from your textbook, and I want to just show you here. Here we have neon. So neon has a total of 10 electrons, and the first 2 are in the 1s2 orbital, and then the next 2 are in the 2s2 orbital. And then lastly, we have 6 left over, and they're essentially in the p orbital. Now, to represent the valence electrons, now notice we're not looking at the s orbital in the first energy level. We're actually only looking at the last 8 electrons that are in the neon's valence electrons. So here we put 2 dots per valence electrons. Now if we go up to boron here, boron has a total of 5 electrons. So notice that with boron, there's 2 electrons in the first orbital, and then we have 2 electrons in the second orbital. Now we're kind of going to ignore the electrons that are in the inner orbital. We're going to only look at the electrons in the outer orbital. And notice that there's a total of 3. So we're going to draw the 3 dots around the element symbol to represent the outer electrons. So what I would essentially do is just look at what is the highest energy level, and we're only going to count up the electrons that are found in that s and p orbitals. Okay, so arrangement of electrons in atoms is called electron configuration, and they are determined by Aufbau's principle, Pauli's exclusion principle, and Hund's rule. Now we look at the outer electrons of valence electrons, and the reason why is we're eventually going to use that when we look at chemical reactions. So please remember that electron configurations can be represented by orbital diagrams, electron configuration notation, and dot diagrams.